Hello, this is the next video in a playlist that I'm calling General Linear Models Design of Experiments. And this is part 8 of an 8-part mini-series in balanced two-factor factorial designs with interaction. And here we're going to illustrate in the R statistical software what we did in parts 1 through 7. We're going to illustrate it with an example from the Douglas Montgomery book on design of experiments. And it's example 7.1 where they look at the life in hours of a battery. And the device can be, and the battery is used in the device, and the device can be used in extreme temperatures, cold and heat, measured in Fahrenheit. And they're also, they're going to try to control for the material type and the temperature, and then look at the battery life. First line, I remove all elements from R. I load in the data and let's view it. And so on the right side here, we have Y, which is battery life, material type 123, temperature, which is 15 degrees Fahrenheit, 70 and 125. And now let's create a design matrix out of this. Factor A, we're going to call material type. Factor B, we're going to call temperature, and we're going to do 4 replications within each. So we're going to store the battery life in a variable called capital Y. We're going to have a design matrix piece for material type. And if we look at just material type, it looks like a one-way, fixed effects ANOVA. And then let's create a column space for factor B, the interaction effect. We need a column of ones for the grand mean, and then we're going to put them all in a matrix called X, and it looks like this. And unfortunately, it wrapped in R because so the first column is all ones corresponding to the mu parameter. The next 3 correspond to factor A. The next 3 correspond to factor B, and then the next 9 correspond to the interaction space. And you're going to hear my cat in the background. Always seems to come in when I create videos. Now let's create the perpendicular projection matrices for these, and I need a generalized inverse, so I need to load the mass library. There's the identity matrix, J, which is the projection matrix onto the column space of ones, MA, MB, MAB, and M. And M is the perpendicular projection matrix onto the whole column space, and then these create the ones previously, J, MA, and MB and MAB. They create perpendicular projection matrices onto those subspaces of the column space. And in this design, it actually, the M and M dot AB are the same. They project onto the same column space. And if we test that, it comes back true. Now, one important component is understanding that if we pre-multiply Y by one of these projection matrices, understanding the structure of the mean vector that we get back. And so that's what we want to do. So I create, I calculate the mean for material type 1, 2, 3, and 4. And notice the mean vector is just repeated, of those means. And then if we do that for the column space associated with B, or factor B, then here are the means for each temperature. And then this mean vector just repeats those means. And if we do the interaction subspace, here are the means for each temperature and material type. And then notice that these means here will be repeated 4 times throughout that whole mean vector. And then J times Y should create a constant mean vector of just the grand mean, and it does. Now let's partition the sums of squares. Now I do this twice here, so I'm going to call it model 1 and model 2, and I want to show you how I enter the data. The first one, I put material type first and then temperature, and then the next one I put temperature and material type. And why is that important? Because in R, it calculates type 1 sums of squares, so the order at which they come into the model is important. But since this is a balanced design, all those type 1, 2s, and 3s sums of squares, and since there's no missing data, type 4 sums of squares are all equal. And that's what I want to show here. So if we look at the summary of Model 1, and we can just look at material type 10684, and then temperature 3919. And then if we do that for Model 2, notice material type is the same and temperature is the same, even though they come into the model differently. And that's very important in R, and I think that's underappreciated for people using R. Now, now I want to derive the sums of squares based on the matrices that we calculated in part 3. And so I'm going to repeat the summary and then the analysis. So SSA is the sum of squares for factor A, which is material type. We have 10683.7, and it just rounds it to 10684. And then if we do this for factor B, we get 3919, which is the same temperature, and then the interaction term, so 9613, and then it's rounded to 9614 because of the 0.7. And then let's do the sum of squares air, and it's 18231, which is the same as when we calculated it, by hand, not by hand, but using matrix theory. And the sum of squares total is I minus j, of course, y transpose I minus j y. And notice that if we add up all the sums of squares that we calculated, that it does equal sums of squares total. Now, let's go through the degrees of freedom. And the degrees of freedom for each is the rank of that matrix in quadratic form, or the sum of the diagonal elements. So here's the model summary again. So the degrees of freedom for factor A is the rank of MA minus J, which is 2, and you see that on the right. Or we could actually just take the diagonal elements and then sum them, which is what this next line does, and we get 2. And so since both methods are equal, I'll just do one of those methods, and we'll just look at the rank of each of those. 2, 4, and it should be 27. Yep. Now, whenever you're doing hypothesis tests, you need to make sure that the sums of squares error is independent of that numerator. And since we're looking at quadratic forms, it's actually the product of those two matrices, in quadratic form. And if they're equal to the zero matrix, then they're independent. And that's mainly, because we're assuming y is multivariate normal. And so that's what this step is doing, is comparing each of those products with the zero matrix, and it is true in each of those cases. Now let's calculate the mean squared error for each of those. And again, here's the summary. And the mean squared error is the sum of squares divided by degrees of freedom. And so the mean square for factor A is 5341.8, which is rounded to 5342 in the table. Mean square for factor B is 19559.3, and it's the same. And if we do it for the mean square for the interaction term, 2403, and we get 2403 in the table. Mean squared error is 675. And to me, this is so cool because we're using matrix theory to reproduce what are, outputs. Now the F test statistic is the mean square for factor A, factor A divided by the mean squared for mean squared error. And so we get 7.9, and we get 7.9 right here. So if we look at factor B, we get 28.96, and it's the same. So let's look at the F value for the interaction term. We get 3.559, which rounds to 3.560. And of course, I did these in the wrong order. You always want to test interaction term first. I'm just illustrating how that we calculate these using matrix theory versus, letting SAS do it. Now, the p-value is just the test statistic, and calculate the, the area in the tail from that, and we get 0.0019. And it's the same as this one. Let's look at factor B, and it is the same. The interaction term, same. Isn't that so cool? Now let's look at contrast. And in here, we want to set up a contrast for material, so factor 1 of 1, 2, and -3, and then a contrast for temperature of 1, 0, -1. And the way you have to do it, you have to create these contrast interaction terms. And so and actually this is one approach, it isn't the only approach. Then you take the Kronecker product of these. So you take this times the first component, and then you get 1, 0, -1 back. And then you take this contrast times 2, and you get 2, 0, -2. Then you take this contrast times -3, and you get -3, 0, 3. And then that becomes what we test. It's our estimable function in the interaction space. And so we just take these that we got from the Kronecker product and then put them in here. Now, this next statement, I'm using what we did in a little 4-part mini series on estimability. If you take C1 times the generalized inverse of X transpose X times X transpose X, and if we get the same linear, combination back, then it's estimable. And we do. We put it in that crazy formula, and we got the same thing back. And so then, and to show you that they're different, if we would have set up the contrast for material of 1, 0, -1. So remember up here we let temperature be 1, 0, 1. Here we're letting material be 1, 0, 1. And then the contrast for temperature will be 1, 2, -3 instead of material up here. And so I'm just showing you the correct order and to do this Kronecker product. So then you take 1, 2, -3 times 1, and then you get the 1, 2, -3. Then you take the 1, 2, -3 times 0, and you get all zeros. And then the 1, 2, -3 times -1, and then you get this. Then you set up your, your vector here, and you put it in the interaction space, right? All these zeros are, the first 0 is associated with the mu parameter. The next 3 are for factor A. The next 3 are for factor B. And then the next 9 are for the interaction space. So let's see if that is an estimable, that the linear combination of our parameters produces an estimable function. We put it in this crazy expression, and notice we got it back. 1, 2, -3, 0, 0, 0, -1, -2, 3. So it is estimable. Both of them are, C1 and C2. Now, this here, the fractions, not the fractions, but this whole statement, it produces the row 1. So it's the linear combination of our design matrix that's going to produce that C1 vector. And then this statement produces the estimate of that linear combination. So it's 114. And then the variance is this, of the variance of that estimable function, or the contrast. And these formulas are derived in that little mini series on estimability. And then this is the sum of squares associated with that estimable function. And here's the F test statistic associated with it. And then for contrast 2, it's the same thing. That is the row 2 so it's the linear combination of the design matrix that produces that the C2, or that, that vector that we want to take times the parameter. So then this is the estimate of that estimable function. This is the variance associated with it. And then the sums of squares associated with that second linear combination. And then this would be the F value, the test statistic, if we want to test to see if that is significant. Okay, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.